just looking towards that review packet from class today, we did get to the model. We know that we have to label the mean and the standard deviation, whether we put this end model somewhere or we label it right on the picture. We know that within one standard deviation of the mean is 68% of our data. 2 standard deviations from the mean is 95% of our data. And then 99.7% of the data is made up with all the data within 3 standard deviations. So when we look at part B, we're looking just at our 95. So our pieces of 15.6 to 16.8, that's each 2 standard deviations, one to the left and one to the right of the mean of 16.2. Now, we're just started talking about the third quartile. And remember, the third quartile makes up a total of 75% of our data. So when you already know the percent, that's when we use that inverse norm calculation. So it reads everything from the left to the right, which is what we want in this case. So I'm going to put 0.75, and we get approximately the value of 0.67. That is our z-score. So we can use that z-score to calculate the exact value, which we don't know, if we know the mean is 16.2 and the standard deviation is 0.3. If we calculate this, we'll get about 16.401. Okay? So anything up to that amount, that's where our third quartile is. So 75% of our data is represented up till 16.4 of our glasses filled. So the ounces inside. In part D, if the glass will actually hold 16.7 ounces, we want to think what percent of the time we're expected for it to overflow. So now we have to calculate our z-score first. So we take our value of the 16.7. We're using that same mean of 16.2, and it's all over the standard deviation. So we're going to get 1.67. Now it's time to write that probability statement. Now overfill, our z-score is probably going to be, we want something bigger than this. So we want bigger than what we got. Oops. And we calculate that into our norm CDF. When we calculate that in though, we end up with a value of about 0.047. And we can even add like the 4/6 still. And when it asks about that, remember we would write our sentence in here according to the normal model. So this is on our normal curve. We would expect the glass to overfill approximately 4.7% of the time. So remember, all of these should technically have a picture and have a phrase that go with it according to the normal model when we're dealing with the normal model given up top. I'm not going to write it here, but write that as note for yourself. And if you're ever in doubt, draw yourself a picture and and make sure you're writing some kind of statement in context about what just happened. So if all else fails, make sure you make those notes for yourself. Now in part E, the manufacturer wants to reduce the overflow rate, only by 1%. Now again, remember, overfill is probably to the right of what I'm thinking of here. So if I had my curve, sorry about that. So we'd have that 1%, but this 1% is the overflows over here. So that means we're shading everything. So when we talk about inverse norm, I remember it always reads from left to right. I'm going to put 0.99 in there. And when we do that, it's going to be 2.33 about. Now, if that's my z-score, I'm going to just use that to do my calculation here. So we're going to have 2.33 is equal to, we're keeping everything else the same. So it's building right off. We're going to keep that 16.7. Subtract that 16.2 of the mean. We're trying to figure out what our standard deviation has to be. And we're just going to solve for the standard deviation in this case. And when we solve, so we subtract, cross multiply, we're looking at 0.214592. Okay, so our standard deviation is here. Now, this part directly ties into the following part of F. Briefly explain what the change in the standard deviation means in this context. Don't forget context. Okay, so we always want to keep context involved. So I would say something like, compared to the original standard deviation of 0.3, there's less variability in the soda that is dispensed. Okay. So again, compared to the original, there is less variability, because remember, standard deviation always refers back to that variability in the data, because there is the changes. And I don't want to forget to throw context in there. So all these questions that we see should involve some kind of sort of context. But in that, remember, standard deviation is like how far away it is from the mean. If we have a bigger standard deviation, there's more variability in our data. So if it's closer to the mean, if we have a smaller standard deviation closer to 0 there, that means more of my data is closer to the mean. So the smaller it is, the less variability there is. Now, G is a little bit different. So in this case, we have two big parts that we really got to look at. The first one is that we want 98% of their glasses will be safe from overflowing. So let's picture what that is. 98% will be safe from the overflow. Okay, so we have 98% of our data is made up here to the left. Okay, we don't know what our mean is. That's what we're looking for. But 16.7 is the size of the cup that we're not overflowing against. So everything that I didn't shade in is what would happen if it overflowed. So this is making up 0.98 of our data. So same as any other time, we know a percentage. I'm going to do my inverse norm of 98 because we read it from the left to the right. And we end up with about 2.05375. Okay. And I can set that up. I don't have our mean or our standard deviation yet, but imagine if we plug that in, we would take our z-score. It would be equal to that 16.7. Subtract, let's just call this mu over our standard deviation. So I can't really do much with that. Maybe I can cross multiply and leave it as our z-score times that, standard deviation, not theta. Go to 16.7 minus mu. So I'm going to leave that alone for a second. We're going to come back to that in a moment. So that's all just for if we had the 98% of glasses that are safe from overflow. The other part that's in here, though, is 70% will not have more than 16 ounces, or excuse me, will have more than 16 ounces to reduce the customer complaints. So I'm going to picture that as well. I have my normal model. We have 16 over here, and we want more than 16 ounces in here to keep the customers happy. And this is making up 0.7 of our data. So remember, we read it left to right, though. So this part that's not accounted for when we do inverse norm, we're actually going to do it of 0.30, because we always read left to right. And our inverse norm is going to get us a negative 0.524401. Oops, sorry about that. So I'm going to do the same kind of setup we did for the last one. We're going to take that negative 0.524401 equal to 16 as our value. We don't know our mean or standard deviation, but I'm going to set it up the same way. I'm just going to cross multiply here. Now, the reason why I've done this is I've just done the two parts that are in here. Now, I have to satisfy both. So we might just think of a simple algebra we can use here is I'm going to set this up as a system of equations because to get the solution, I need to solve for both of these. So I'm just going to stack our purple piece right underneath here. So that second part that I calculated, I'm going to have it, oops. So 0.5244401 theta equal to, and remember it's equal to this 16, subtract mu. Now, I only want to solve for one letter at a time if I can avoid that. So I'm going to multiply this whole bottom piece by a -1, which means I'm going to change all my signs here. I'm going to combine like terms to get 2.57816 theta equal to 0.7, and the mu's are going to cancel out there. So now I can at least solve for the standard deviation. So I have that equation. All that's left is to divide both sides. So theta, I'm sorry, not theta. Standard deviation here is 0.27513. Okay. And I'm feeling pretty safe with saying that I can call that 0.27. So once I have one piece of this, now all that's left to do is I can plug into either one. I can go back to this line, or I go back to this line. I'm just going to plug in that 0.27. If I plug it in to solve for mu, we're going to get something about 16.14. So this one was a little bit outside the box there. You want to think that you want to satisfy both, so you want to set it up as much as you can. And then since both things have to be satisfied, we set them equal to one another.